Today's lecture, lecture 4, is going to talk about some properties of estimation, of estimators, of statistics, and then we're going to get to our kind of first method of creating estimators called the method of moments. The first thing that I want to do is I want to start off by giving, kind of revisiting our definition of a statistic. So the original definition we had given of a statistic was just some function of the data. And I want to refine that a little bit more. So our setup is that if we have some random sample from some distribution, f, and f is parameterized by a parameter theta, and theta lives in some universe of possible thetas, we'll call capital theta, and theta is unknown. And our definition of a statistic is going to be a function of the x's whose formula does not involve theta. So let's just write that down. A statistic t is a function of my random sample whose formula doesn't depend on the unknown parameter theta. Right? What we're trying to avoid is that if I have, maybe a random sample that is from some normal population, then t equals x bar is a statistic, but t is equal to mu isn't a statistic. And we could say neither is t is equal to x bar minus mu. We don't want to count these second two options because it's kind of cheating. We don't know, for example, in this case, maybe what mu is. So let's just say in our situation, mu is unknown. So we don't know what it is. And so ultimately, what we're going to talk about today is how we want to estimate things with statistics. And if we can use the unknown quantities in our statistics, that makes estimating things very easy because I can use my unknown quantity to form an estimator. If you ask me to estimate mu, you might tell me x bar. If I'm allowed to say, well, it's mu, that is my second case here, not a really great estimator. So we're going to ban statistics from having the unknown parameters as part of their formula. Okay, so that's just a little bit of an update on our definition to statistic. It probably doesn't change much because I'm sure no one had thought of doing that because it's a kind of silly thing to do. It comes in handy for the next thing we want to talk about. And so we're going to define what's called an ancillary or ancillary quantity. And an ancillary quantity is basically the opposite of a good statistic. And we'll talk about what I really mean by good statistic a little bit later in the lecture. But what we're thinking is that we're going to create statistics to estimate the unknown quantities. parameterizing our distribution, parameterizing the data. And an ancillary quantity is a quantity Q, or Q of my x's, so it's a function. Maybe we should write it is a function of my x's. Let's call it Q for quantity, that doesn't depend on the unknown parameter, period. So that's our definition of ancillary quantity, right? It's basically the opposite of a good statistic, because any quantity that doesn't depend on the unknown parameter. And maybe I should be more specific. It's any kind of quantity, it's any function of my data whose distribution doesn't depend on the unknown parameter. So let's look at some examples. We can create some ancillary quantities. Let's say, again, I have my favorite normal model. Then we know from our second lecture that if my data comes from a normal mu sigma squared, x bar will have a normal mu sigma squared over n distribution. So if I let Q be x bar, let's say minus mu over sigma over square root of n, this is ancillary, we might say, to mu and sigma squared. Why? It's not too hard to show that Q will have a standard normal distribution. So the distribution of Q doesn't depend on mu or sigma squared. I basically excised mu and sigma squared from the distribution, and so Q is ancillary to them. Notice, however, this, we're calling this an ancillary quantity. I didn't say it has to be a statistic. And our definition of statistic would, our kind of updated definition of statistic would require that the formula doesn't depend on any unknown parameters. I'm only calling this a quantity at this point. And notice my quantity here depends on mu and sigma squared over and sigma squared, right? The unknown parameters. So this is not a statistic. Let's say because it depends on mu and sigma squared. Nonetheless, it is ancillary, kind of an ancillary quantity, because the distribution doesn't depend on them. You can furthermore define an ancillary statistic, which is, we could say T is an ancillary statistic if it is an ancillary quantity and also a statistic. So Q above would not be an ancillary statistic. The idea with an ancillary statistic is that T doesn't involve my unknown parameter, generically theta, in its formula, nor does it involve it in its distribution. So ancillary quantities are a bit strange. Notice here that our definition of an ancillary quantity or statistic depends on the probabilistic model and theta. So it depends on, it depends on what is unknown. So it depends on the model and what is unknown. So for example, if we're going to beat this to death, but if I have, again, a normal mu sigma squared model, I really have to specify what's known or unknown. So if I say with mu unknown, but sigma squared known, then let's say t is equal to well, let's not try on the fly come up with an ancillary statistic. But one could imagine that I have a choice. I could set up this model where mu is unknown but sigma squared is known, or where mu is known and sigma squared unknown. And this will change potentially what would be ancillary to mu or sigma squared, because I would be allowed certain things. If I wanted an ancillary statistic and I said I know sigma squared, well, I could involve sigma squared in that statistic. If I say sigma squared is unknown, I can't involve it in the formula for it to be a statistic. So always in the back of your mind, there is a probabilistic model with some generically theta that is unknown. And you do have to actually be careful to pay attention to what is unknown, because it can change how some of these properties work. Let's look at an example of an ancillary statistic. So if I let's say my data comes from a normal theta 1 distribution. So here, generically theta, I'm not going to write it every time, but theta is unknown, right? And define the range R to be the maximum minus the minimum. So that's our classic definition of the range. And the question is R ancillary to theta? Well, I probably wouldn't be asking if it wasn't. It is ancillary to theta. But that's not obvious, because certainly the distribution of the maximum depends on what theta is, and certainly the distribution of the minimum depends on where theta is, right? If I take a bunch of normal data and I say its mean is, if theta were 0, if the mean of the distribution was 0, I wouldn't expect a maximum above, 4 very often. But if I said that theta were 10, I would always expect my maximum to be above 4, because on average it's going to be about 10. So certainly the maximum and the minimum depend on theta. And so the question is, if I take the difference, is that ancillary to theta? So notice that what we can do here is I can write my xn's as some zn's plus theta, where my zn's are IID normal 0, 1. Right? If I take a normal 0, 1 and I add on theta, it would be normal theta 1. So my xn's can all be equivalently decomposed as some standard normal zn plus some shift theta. And similarly, this means that my maximum that the maximum of the x's is just going to be the maximum, how do we want to write this? The maximum of the z's plus theta, and the minimum of my x's is going to be the minimum of my z's plus theta. Why is that true? Well, if you think about the data generation process being, I first generate the z's and then I add theta to them. Well, if the maximum of the z's is 5 and I add theta to that, then the maximum of the x's is 5 plus theta. And similar for the minimum. The minimum of my data is 1, then the minimum of the z's is 1, then the minimum of the x's is 1 plus theta. So the maximum of the x's and the minimum of the x's can be written as the corresponding statistic for the z's plus theta. What this means is that my range, which is my maximum minus my minimum, can be written as the maximum of the x's plus theta minus, the maximum of the z's plus theta minus the minimum of the z's plus theta. And of course my thetas cancel out, so I get that this range of my x's can actually be written as the range of the z's, as the maximum of the z's minus the minimum of the z's. And why is this important? My z's, remember, are normal 0, 1. So they don't depend on theta. So the distribution of the z's doesn't have anything to do with theta. So certainly the distribution of the maximum or the minimum of the z's has nothing to do with theta. And the difference of them is not going to introduce theta somehow. And so our punchline here is that the range is ancillary to theta for this example. And that makes some sense. The range is basically a measurement of spread of the data. And theta is the center location. So the measurement of spread doesn't tell me anything, is ancillary to the mean. You can think of some other measurement of spread that might be ancillary to the mean also. We'll get there. So this is an example of an actual statistic, right? This is a statistic. Indeed, it's an ancillary statistic. It is a statistic that is ancillary to theta. The reason it's a statistic is it doesn't involve theta in the formula. Nonetheless, its distribution still doesn't depend on theta. So nothing to do with theta at all. So why are we studying these? Just to discuss why we're studying these, we want to talk about two more concepts here. And you might see these in the book. In any of the books I've suggested at various points. We're not really going to get into these topics. It's they're more kind of graduate level topics, so we're not going to get too deep into them. But it's worth mentioning them in case you see them. And it turns out we don't really need to worry about them too much for this class. So the first concept that I'm just going to make you aware of is what's called a minimal sufficient statistic. So we had this definition of what a sufficient statistic is. So by example, if, again, my data potentially came from like a normal mu, let's say 1 distribution. So oftentimes you'll see people do things like this where they say normal mu 1. That's basically because they don't want to have to write normal mu sigma squared, where mu is unknown, but sigma squared is known, right? It's basically the same thing. So whenever you see someone writing this thing normal mu 1, it's because they only want to consider the family of normal distributions parameterized by just the mean being unknown. Anyways, as an aside. Assume I have some normal data. We showed that x bar was sufficient for mu. So we could say t is equal to x bar. My statistic t equals x bar is sufficient for mu. what about a two-dimensional statistic? T equals to x bar, and then let's look at x bar to the third power. Is that sufficient for mu? So the gut instinct here should be that sufficiency of a statistic means that that statistic contains all of the information about the unknown parameter. So if x bar contains all the information about the unknown parameter, then certainly x bar and some other stuff is going to contain all the information about the unknown parameter. I can add on other information in the form of x bar cubed if I want. It's not actually going to help me. I already know of everything about my parameter mu, or all of that's kind of encapsulated in x bar. Nonetheless, it doesn't actually hurt. It doesn't make it not sufficient to add on extra information. It doesn't actually get me anything, but it doesn't hurt. And so, yeah, I could believe that x bar cubed is arbitrary. I could add anything else. You know, your birthday, you know, your favorite color. It doesn't detract information. It doesn't really add much useful information because all the information is already contained in x bar. So if I have a sufficient statistic, then I can always tack on other information. So in this case, yes, I can always add on information. But somehow this seems wasteful. And indeed it is, and you can formalize this in terms of what's called a minimal sufficient statistic. And a minimal sufficient statistic is a sufficient statistic that contains no extra information. No extra. So let's say sufficient, but no extra information. A minimal sufficient statistic, if you remove any part of the statistic, it won't be sufficient anymore. And there's no fat to trim, as it were. So that's one concept called a minimal sufficient statistic. And that one's somewhat intuitive, that we'd want to find minimal sufficient statistics. We want to be as kind of parsimonious as possible. The other concept, let's just call it a concept here, is a complete statistic, or a complete sufficient statistic. And this is much more of a graduate level concept, and we're not going to talk about it too much. I'm going to alert you to its existence. But a complete sufficient statistic is, it turns out it's related to minimal sufficient statistics, and in many cases they are the same thing. But a complete sufficient statistic basically means, let's say T is complete if I can't make a ancillary statistic from T. So a statistic is basically complete if there is no way to make a statistic from T that doesn't contain information about the parameter. I can't make it ancillary. So a complete statistic or complete sufficient statistic basically means I cannot. It's so powerful a statistic you can't in any easy way get rid of its dependence on theta. That its distribution will always in some way depend on theta. unless I do something really trivial. And there's no kind of non-trivial way to turn it into something that doesn't depend on theta. Completeness is a super deep topic. Deep. It has a bunch of implications, a bunch of really cool ways to interpret it. I'm not even going to give kind of a mathematical definition here. All I'm going to say is that it has a lot of connections to analysis and to functional spaces, and it is connected to ideas of uniqueness, or what statisticians call identifiability. And basically, what these concepts mean is that the statistic, the complete statistic T, is rich enough to to figure out theta, or to separate different values of theta. So the whole idea in this class is that we have a probabilistic model and we have some unknown theta. And if you were able to generate data where you couldn't decide one way or another if it's more likely that the data comes from one value of theta versus another, that would be a bad situation, because you wouldn't have a good way of saying, well, I should choose this as my estimate of theta versus something else as my estimate of theta, because you couldn't kind of figure out which is the more likely value of theta. That would be what was called a non-identifiable model. And this kind of corresponding concept for statistics, which is basically called complete statistics. And complete statistics basically have enough richness, they contain enough information in a fairly complicated kind of real analysis way, that they are able to kind of form a basis of a certain functional space, and they are able to say if it's more likely the data comes from one model, one value of theta versus another value of theta. Okay. So neither minimal sufficiency nor completeness is something you actually need to memorize for this course or write down ever. I'm mentioning them because A, it's interesting, and B, you might see them in one of the books or some readings you'll see somewhere. The reason we don't need to worry too much is the following theorem, which says we don't need to worry too much. And the theorem basically says that if my data, my random sample, comes from some f theta, and f theta is an exponential family, so that f theta of x, what did I say? It's is some h of x, some c of theta, exponential of t of x transpose, t of x times w of theta. So if my data comes from a one parameter, so theta is just some number, my data comes from a one parameter exponential family, then t, this value, we saw last time that it is sufficient, but indeed t is actually sufficient, it's minimal sufficient, and it's complete. Then, so let's write that. It is sufficient, and t is 1, sufficient for theta. Indeed, it is minimal sufficient for theta. And 3, it is complete. And honestly, we're not going to, beyond this lecture, pretty much not going to talk about minimal sufficiency or completeness. We're going to work a lot with exponential families, and the reason I spent so long talking about this weird kind of parameterization of exponential families is that everything works nicely for them. If I have data from an exponential family, this t here is a sufficient statistic for theta. It contains all the information for theta. It does not contain any extra information. It is minimally sufficient, and it is complete. It is rich enough to kind of figure everything out in the problem. So this is the don't need to worry too much theorem. But nonetheless, you might see minimal sufficiency or completeness come up if in one of the books, or you do some Googling around outside the course. And for one parameter exponential families, don't need to worry that much. Okay, so we had alluded to the fact that minimal sufficient statistics, complete statistics, or generally sufficient statistics were kind of the opposite of ancillary statistics. So we had alluded to the fact that sufficient contains all info about theta, and furthermore that ancillary contains no info about theta. And so somehow these are opposites. And the theorem, which is called Asus Theorem, mathematically or statistically codifies this. And the statement is super simple. It says that if T is sufficient, and S is let me be more specific here. If T is a sufficient statistic, we can't have any dependence on the unknown parameters, and S is an ancillary, again, statistic, can't depend on unknown parameters, then T is independent of S. That's all. So it kind of mathematically codifies this relationship in which sufficient statistics contain all the information about a parameter. Ancillary statistics contain none of the information about the parameter, and they're opposites. They're actually independent of each other. All right, they're both statistics. They're both random quantities, and so they're independent. So this brings us to a theorem that we had stated in lecture 2, and we had said that if we had data that had a normal mu sigma squared distribution, my claim was that x bar was independent of my sample variance, s squared. We can now actually prove this in very short order. How do we prove that? What we can say is, remember that x bar we showed is sufficient for mu, and if we look at s squared, another part of that theorem said that if we looked at n minus 1 over sigma squared times s squared, this had a chi-squared distribution with n minus 1 degrees of freedom. another set of different ways that S squared has some distribution that is basically whatever we get if we multiply a chi squared by sigma squared over n minus 1. So that's a bit of abusive notation. But what I mean on the right-hand side here is that if I had a random variable that's chi squared n minus 1, then multiply by sigma squared over n minus 1, right? So effectively, S squared has that distribution. It's some type of gamma is what it is. It's a chi squared is a special case of a gamma. And if we notice that this doesn't depend on mu, in fact, neither side of that depends on mu. So S squared does not have mu in its formula, and its distribution has no dependence on mu. It depends on sigma squared and the sample size, but it has no dependence on mu. So x bar is sufficient for mu, and my sample variance is ancillary to mu, QED. X bar is independent of S squared. There are other ways to prove that theorem. That is the nicest way of proving it, because you can basically do it in about 2 lines. So the theorem is called Asus Theorem, which says that sufficient statistics are independent of ancillary statistics. Yeah, that can be used to show that x bar is independent of S squared. Okay, so we're going to change gears a bit here now. We now talked about statistics, we talked about some normal statistics, we talked about some properties of statistics, mainly sufficiency. We talked about ancillariness, minimalness, completeness, and we had this nice theorem. We're now going to change gears to what's called point estimation, which is basically a fancy way of saying estimation. How do we form estimators? And eventually we're going to get to how do we form good estimators. So again, our setup here, which is basically set up for every, we can basically add this setup to every sentence in this whole course, which is that, have some data, comes from some distribution, parameterized by some parameter theta, and theta is unknown, but it lives in some larger set of possible thetas, capital theta. We could maybe give a definition here. A point estimator is kind of the point estimator of our parameter theta is going to be basically an estimator of theta, is just a statistic, and typically our notation is if we're trying to estimate a parameter theta, our estimator is called theta hat, or it's theta hat of our random sample. So a point estimator is just a statistic. There's some kind of pedantic terminology here, which people don't actually follow, but I'll write it down because occasionally you run across it, which is that theta hat, right? So theta hat is a function. Typically, it goes from the Rn, the size of our sample, to some lower dimensional space. Typically d is 1, right? It just summarizes all of our sample into one number. And so that's a function. And theta hat of our random variables, of our random sample, is called an estimator. And an estimator is a random variable. Theta hat of a particular realization of our random variables is called an estimate. So this is not random. Now you occasionally come across this terminology, so I thought I'd let you in on it. So an estimator is basically the random variable version of an estimate, which is a particular realization of our estimator. So the question that we want to answer in this course, we want to answer a couple things. One is, how do I construct estimates or estimators? And two, how do I know if the estimator I construct, that is one, is good? I don't know if the procedure I come up to develop an estimator is actually a good idea. So we're going to learn a couple of ways of constructing estimates or estimators, and we'll talk about evaluation of them and how do we determine what the best way to estimate something is. So our first method for constructing estimators is called the method of moments. And so we should do a real quick review of moments. So if you recall from probability, the rth moment of a random variable, let's call it x, is typically, or I'll denote it as mu sub r, and this is defined, that's supposed to be DEF, defined to be the expected value of the rth power of x. So x is just a univariate random variable, and the rth moment of x is the expected value of its rth power. We can also define the rth sample moment of a random sample, let's say x1 to xn. The rth sample moment of this random sample is, and let's say instead of mu sub r, let's call it m sub r, and this is going to be defined. Basically, we're going to define it as the average value of the rth power of our samples. So the sample moment is like, or the rth moment of some random variable is the expected value of its rth power. Expected value is kind of like an average, and I mean, it indeed is basically the definition of the population average. And so the sample version of that is the average of the rth powers of our random sample. So basically, the idea is we're replacing the expected value of some x sub r with the average of the powers of our random sample. And you might expect that if we have a large enough sample, that the sample moment will start to look a lot like the kind of population rth moment. That is, it's going to be a good approximation of the underlying true expected value. And that's generally true, right? If you ever want to approximate an expectation, you basically approximate an expectation with an average. Think about a normal distribution. There's some expected value, we call mu, and the way we estimate, we approximate the expected value is we look at the sample average. So the method of moments the method of moments is just going to say, okay, well, these things should be close, so we should set them equal to each other, and we might be able to get to back out through kind of solving some equations. We might be able to back out an estimator. Let's look at a concrete example of that. So, right, so the first estimate, the first moment of a distribution is called mu1, and the first sample moment is basically x bar. The second population moment, expected value of x squared, and the second sample moment is going to be basically the average of the squares, and so forth. The third moment is going to be expected value of x cubed, and the third sample moment is going to be the average of those powers. Notice here that if I look at the expected value of MR, right? So MR, you can think of it as a random quantity, right? Because the x of n's are random. The expected value of the rth sample moment is the expected value of 1 over n, sum of these things to the rth power. And expectation can be pushed through. Certainly I can bring out that 1 over n. Certainly I can bring out that sum. And I can push it through like that, because expectation is linear. And so I get 1 over n, the sum of that. But of course, the definition of the expected value of x to the r is just going to be mu r. That's the rth moment of the x of n's. And so I have, at the end of the day, just mu sub r. So at least on average, the sample moment is approximately going to give me the true population moment. And so the method of moments is basically going to say, these approximately are going to be equal. We should set them to be equal. You pick your favorite number r. The first moments, the second moments, depending on exactly what your need for the problem, but you set them equal and you solve for mu, and that will give you something. So, concrete example here. This is all a bit abstract. Let's look at a situation where we have our favorite normally distributed random sample, and here I want estimates for mu and sigma squared. So I'm assuming they both come out unknown. I want to estimate these. So MOM, method of moments. Method of moments is going to work like this. First thing I'm going to do is calculate the first two moments of my normal mu sigma squared distribution. Calculate the first two moments of my underlying distribution. So mu1, so here we're basically saying we're kind of envisioning some x that's distributed normal mu sigma squared, and mu1 is of course the expected value of this thing, which is mu, not surprisingly. Mu2 would be the expected value of this squared. Well, what's that? Well, we can use our variant shortcut formula to show that it is if I rearrange it, it's the variance of x plus the expected value of x squared, right? This comes from the variant shortcut formula, which says that the variance of any random variable is the expected value of the square minus the square of the expected value. And so I can rearrange that formula and I get that the expected value of x squared is just the variance plus, whoops, someone should call me out on that, plus the square of the expectation. the variance of my normal mu sigma squared is sigma squared. The mean is mu squared. So the first moment is mu, and the second moment is sigma squared plus mu squared. Our second step for method of moments is to say that approximately it should be that mu1 should approximately be equal to the sample moment. M1 should be approximately, or should approximate, the true population moment, mu1. And my second moment should be approximated by my second sample moment. And if I do that, what do I get? Well, this first one, the first moment mu1 is just mu, and the first sample moment is x bar. So I'm going to guess that a good estimator for mu is x bar, because if mu1 is basically this first sample moment, that would say that I should estimate that mean as the sample average. The second relationship, if I'm going to say that I'm going to approximate my second moment by the second sample moment, this would say my second moment is mu squared plus sigma squared, and my second sample moment is 1 over n, sum of the xn's squared. And what I want to basically do is, I already have isolated mu, so I'm going to say x bar is a good estimator for mu, and I want to isolate sigma squared. If I isolate sigma squared, this sigma squared would be this thing minus mu squared. But of course, if mu is x bar, then I can replace mu squared with x bar quantity squared. And indeed, if I do that, one can show, and you can think about how to do the algebra, that one can rearrange, this is basically the average sum of the squares minus the average squared. This is equivalent to the following: 1 over n times the sum of the xn's minus x bar squared. And so that would be isolated sigma squared. So I could say, well, that should be an estimator by this logic. And all my logic is that the sample and the population moment should be kind of equal. If I were to set them to be equal, I would say that mu should be approximately x bar, and sigma squared should be 1 over n times the sum of the deviation squared. So this looks a lot like s squared with n minus 1 in the denominator, and it basically is, but replacing n minus 1 with n. So and yeah, that's not going to make a huge difference. A huge difference for large n, and n minus 1 are very similar. But there's no reason to say that we have to use n minus 1 in the denominator to estimate sigma squared. In fact, the method of moment says it's pretty reasonable to use 1 over n in the denominator as an estimator of sigma squared. And I could even call these things mu hat as x bar. And let's leave some room here. I could say sigma squared hat would be the estimator of sigma squared. And those seem reasonable. And so the method of moments, all it's doing, just review this problem, is I'm going to calculate my population moments, and I'm going to say those population moments should be approximately equal to the sample moments. And that's going to give me, in this case, two equations with two unknowns, the unknowns being mu and sigma squared. I solve for mu and sigma squared, and in terms of the x's, and I get formulas for mu and sigma squared in terms of the x's, and I say, Bob's your uncle, those are my estimates. So that's basically the method of moments. So we can formalize that a little bit. I mean, frankly, the discussion I just had is probably the easiest way to understand it, but let's just write down a little bit more formal of a definition. So method of moments. And the method of the moment works like this. I have my data, my favorite setup comes from some distribution, and theta is unknown. And in this case, in fact, we're going to say that theta is, some k-dimensional parameters. Let's say theta or k-dimensional vector. So it's potentially multiple or maybe we should write like this. It's in some big set theta, which is a subset of Rk. Okay. So my parameter is actually a vector. I have multiple parameters. So like in my previous problem, I had mu and sigma squared, so I had a two-dimensional parameter vector. In this case, I could have some k-dimensional parameter vector. And what we're going to say is that the population moments of my distribution, f theta, are generically mu1, mu2, ... all the way up to mu k. So we take k of them. And the corresponding sample moments are, let's again call them m1 up to mk. So you'll notice in the previous problem I had mu1, mu and m1 and mu2 and m2 because I had two unknown parameters. But generally, if we have k unknown parameters, I'm going to look at the first k population moments and the first k sample moments, and assuming, it says assuming, basically the method is going to assume that m1 is approximately mu1 and m2 is approximately mu2 and ... and mk is approximately uk. Then we form the set of k equations in k unknown, where we set m1 equal to mu1, right? So mu1 is some function of my, let's say f1, of my unknown collection of k parameters. And then form a second equation where m2 is equal to mu2, but behind the scenes, mu2 is some other function, potentially different, of my k unknown parameters, ... all the way up to mk, if we set that equal to mu k. But again, mu k is some function of my thetas, right? So these are all I'm writing here is that the mu's are functions of the thetas, right? And the m's are functions of the x's. And then we solve this set of equations. That's supposed to read equations. All right, the set of k equations and k unknowns. So here my unknowns are going to be, I guess you could look at it either way, couldn't you, right? I guess you would say the thetas here would be the unknowns. You know what the x's are. And we solve these set of equations for the thetas in terms of the x's to get our method of moment estimates, or estimators, theta 1 hat, theta 2 hat, dot, 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 of the theta k hat. So it's kind of a lot to write down, but basically all you're doing is if I have k unknowns, I set up k equations where the m's equaling the mu's. M's are a function of the x's, the mu's are a function of the thetas. So we have k equations, k unknowns. You solve for the k unknowns, and the solutions are basically tell us our estimators. It's really abstract to write down, but it's quite simple as we saw in the previous example. So let's just continue, and I think for the kind of rest of the lecture, let's just do a bunch of examples, because really that's how you learn this stuff. So here, let's assume that our data, maybe our data comes from a binomial distribution with the number of trials k and the probability of success p. And let's find method of moment estimators for k and p. So how do I do this? Step 1, population moments. Right, so if I had a random variable x, which was binomial kp, then mu1, which is the expected value of x, should be kp, right? And mu2, which is the expected value of x squared, as before, it's the variance of x plus the expected value of x quantity squared. The variance of x is what? The variance of a binomial, kp, is k, p by 1 minus p, and the expected value is kp, and so if you square that, that's k squared p squared. Step 1 done. Those are the population moments. Form equations. So my first equation is that x bar, which is the first sample moment, should be equal to mu1, which is the first population moment, which is the product of k times p. And my second equation is that I'm going to call this x squared bar, so the squared under the bar, or you could more kind of verbosely write it out. It's the average of the squares. That should be my second moment. And we said our second moment is kp by 1 minus p plus k squared p squared. So 2 equations, 2 unknowns. Step 3, solve for k and p in terms of the x's. And there's going to be lots of ways to solve these problems. So let's say first we can note that according to our equations, x bar quantity squared is kp quantity squared, right? So that's k squared p squared. So if I take x squared bar, so that's the sum of the average of the squares, and I subtract off x bar squared, x squared bar is kp by 1 minus p minus k squared p squared, so that should be left with kp by 1 minus p. I mean, at this point, basically, pause the lecture, solve the equations yourself. I'm going to solve them kind of in my kind of slow, awful way, but there are different ways of solving this. Okay, and so where do we want to go from here? Why don't we do this? X squared bar minus x bar squared divided by, let's divide by x bar. that should give me kp by 1 minus p up top, x bar in the bottom, according to my first equation, so equation 1 here, x bar is kp, so this should give me 1 minus p, hence p is 1 minus x squared bar minus x bar squared over x bar. So I've isolated p, and I can call that p hat. That's going to be my estimator, my method of moments estimator for p. I've got to get m now, and I can be kind of lazy here. Since our first equation says that x bar is kp, then surely if I could say k is x bar over p, and so if I want k hat, all I have to do is take x bar over p hat, and that will give me my estimator for k hat. So it's kind of a cheating way, but that's totally reasonable. Correct that homework, write that in exam. That's fine, right? At least I know how to do it because I could expand out p hat if I really want to in terms of the x's, but I don't want to. So there are my estimates. That's a method of moments estimator for those things. As a side note, so first we're going to talk about a couple ways of constructing different types of estimators, and then we're going to talk about which ones are good. Sometimes method of moments estimators are good. Sometimes they're not so good. These estimates are kind of crap, are not great. Why are they not great? Because notice if m2 minus m1 squared is bigger than m1, so there are some conditions. Could be that the first moment minus the second moment squared, blah, blah, blah. There are some conditions where I could get a p hat that is negative. What? That's true. And that's a crap estimate, right? I should never be estimating my p hat, right? So p is the probability of binomial distribution. That can't be negative. My estimator that I formed through this method of moments approach gives me something that potentially could be negative. So that's not great. So you have to be a bit careful. Method of moments sometimes is okay, but not always. More examples. Let's look at an example. Let's assume our data is Poisson distributed with some parameter lambda, and we don't know lambda. What is our method of moment estimate for lambda? All right, so the previous two problems we've had two unknown parameters, which is kind of where it's interesting because you have a set of equations you have to solve. Nonetheless, you can do an MOM estimate for one parameter families. Sometimes they're kind of interesting. In this case, we can still go through the steps. Mu1 is the expected value of our Poisson, which of course the expected value of Poisson is just lambda, and M1 of course is just x bar. And so step 2 is form the equation, and our equation would be that x bar is equal to lambda, and step 3 is solve for lambda, which is basically already done. Lambda hat is x bar. So that's our method of moments estimator. Our method of moments estimator is x bar. That makes sense though, right? It's totally reasonable. If I have data that's Poisson and I don't know the parameter lambda, lambda is the unknown, is the mean, say, of the Poisson. So let's just estimate it as the average value. Totally reasonable to do. We can look at some variation on this. variation on this. There's no reason that I have to start at the first moment. What if I start at the second moment? The second moment of the Poisson, the second sample moment, is the variance of my Poisson. Here's my horrible notation, plus the expected value of my Poisson. Quantity squared, right? Instead of solving the equation of the first moments being equal, I could solve the equation of the second moments being equal. There's no law that says I can't do that. There's reasons that we'll talk about later in the course why it's not going to be as good of an estimate. But I could. The variance of a Poisson is lambda, and the expected value of a Poisson is lambda. And so lambda plus lambda squared. And I could set that equal to my second moment, which is my second sample moment, which is x squared bar. Hence, a method of moment estimator is lambda hat, which is the cube root? No. Can I even solve that? Yeah. I can get multiple answers, presumably. Well, this is not a great thing. Maybe maybe what we should do here is, instead of using the second moment, let's say let's look at the variance of my Poisson distribution. If I looked at the variance of it, the variance of a Poisson is lambda, so that's easier. And I could set that equal to, instead, set this equal to maybe my sample variance. And so in that case, we could have a method of moments estimator that is the sample variance. So there are kind of a bunch of variations on this. The classic one I taught you up here is the one more or less we're going to stick with, but there are different kind of variations. You can think about your own variations of how to do this. And so, yeah, maybe estimating the variance or the parameter lambda as the variance, or the sample variance, is a good idea, right? Lambda is not only the mean of a Poisson, but it's the variance of a Poisson. And so it makes sense that an estimate of lambda would also be the sample variance, not just the sample average. And we will definitely talk about this later in the course about which one of those two estimators is better. Turns out the mean's better, but we'll talk about it. But there are lots of variations. So for example, here's another problem. I have some data, and my data is from a uniform distribution, a continuous uniform between 0 and some unknown point theta. And here's one way I could do it. I could say step 1, mu1 is the expected value of my x of n's, which is what, for a uniform, it's going to, with a maximum of theta, it would be theta over 2. And m1 is, first moment is x bar is theta over 2, so that's my setup of my equation, which is mu1. And so my estimator would be that, what would I say, theta hat would be, if I solve the equation, that's 2x bar. Okay, so that's one way of estimating, of getting a method of moments estimator. What's another way? Why don't I start with the second moment? No law that says I have to start with the first moment. So the second moment would be well, let's actually use the variance in this case. Let's say the variance of my x's is what, theta squared over 12 for a uniform distribution. That's the variance. And so let's just not call that mu2, but it's the variance. So I could again say the sample variance should be approximately this population variance, which is theta squared over 12. And that would lead me to the estimator that theta hat would be the square root of 12s squared. So, that's another way that we could form a kind of method of moments like estimator. Okay, let's just do one more example here before we end the lecture here, because I think we're kind of at a reasonable point to stop here. So I just want to do a bunch of these method of moments estimators. Here's another example. Let's say that our data comes from some beta distribution with an unknown parameter alpha, but the second parameter beta is known. So here we're basically saying that beta is equal to 1. Then if I want my method of moments estimator, what are my steps? Step 1, what's mu1? What's my sample, what's my population moment? The expected value of a beta, just random variable is alpha over alpha plus beta. In this case, beta is 1, so this is alpha over alpha plus 1. Okay. The second step here is to form my equation. M1, which is x bar, should be mu1, which is, in this case, alpha over alpha plus 1. And step 3 is solve for alpha. And not too hard to do this. We're going to find that alpha hat is x bar over 1 plus x bar. So I'll leave that as a little exercise for you, but that's the answer. If you solve it, right, and not too hard, you multiply by alpha plus 1 on both sides, and then you solve, basically move things over and solve for alpha. So these problems are super easy to generate. They're a lot of fun to do. They're pretty simple, and this is our kind of first technique for generating estimators of things, which is called method of moments, which just is basically using the idea that the sample moment should be a good approximation of the population moment.